third One World Mathematics of Information Data on Signals seminar. Just to remind you how things work, we'll be taking questions through the question and answer utility at the bottom. So if you have any questions for the speaker, just put your question there and one of the hosts will interrupt the speaker or ask her the question after the talk is over. So our speaker today is going to be Anna Gilbert. Professor Gilbert is the Herman H. Goldstein Collegiate Professor in the Math Department at the University of Michigan, where she also holds a joint appointment in the Electrical and Computer Engineering Department. Her many awards and honors include the National Academy of Sciences Award for Initiatives in Research and the Siam Ralph E. Kleinman Prize, among many others. She is well known for her highly influential and interdisciplinary work in computational harmonic analysis, discrete mathematics, compressive sensing, and algorithms more generally. And it is my honor to turn the talk over to Anna to let her tell you about what she'll be telling us about today.
Thank you. Mark, you left off co-advisor of Mark Iwin.
True, but that's one of your very, very least important contributions to the world, I think.
It is a pleasure to speak at this. Early on in this semester, I was asked to give a webinar with a couple of other mathematicians, and this was in February before the world changed. And I thought, oh, this is really quite a strange experience, and I'm so glad that I had that practice because I knew what to do come the middle of March. So I think it's great that you guys have organized this, and I'm thrilled to be here. I can tell you I am not going to talk about pandemics, epidemics, modeling. I'm not going to talk about privacy or stuff like this. I'm going to give a very straight up, boring, ordinary seminar. So this is like a, you know, as normal as we can get right now. So I'm going to talk about three basic problems that have to do with representing metrics, and I'm going to talk about one what we think is fairly general purpose algorithm for solving these kinds of metric representation problems. And we here, this means this is joint work with my student Rishi Santalia, who is absolutely fantastic, along with all of my other University of Michigan students. Okay, there we go. So I'm going to start off with the observation that if you are given data for which the underlying geometry of the data set is somehow distorted, or you're given distance information amongst data points, and those distances have been corrupted in such a way that, you know, maybe those distances actually fail to satisfy triangle inequalities. You know, if you somehow have the wrong geometry for your data set, you're going to have a very distorted view of the world. And to give you a more concrete idea of what it is I'm talking about, I'm going to show you what happens, all kinds of awful things that can go wrong in sort of downstream machine learning algorithms when your data representation, when your metric representation, or when your distances are corrupted. So, you know, many times when we run or when we cook up fantastic data machine learning type algorithms, we begin with distances or similarities or dissimilarities, and we assume that those are fine, that they're accurate, they're correct. You know, maybe there's a little bit of noise in the data, but we never stop to ask, well, what happens to this algorithm if things are really screwed up? So I'm going to show you what happens to one algorithm that is used all the time, and show you what happens if things are screwed up in a certain way. Okay, so I have the Swiss roll. This is a, can you see my mouse? Okay, good.
Yep.
Okay, so you have a data set, and it's a high dimensional data set, and you would like to embed it into a lower dimensional space, like say 2 dimensions, and you'd like to sort of embed it in such a way as to preserve local structure. And I'm not being very rigorous here for a reason. So this is a canonical example. You want to unroll the Swiss roll, or you want to somehow capture its, project it in such a way that you capture its structure. So we start with 2,000 data points in the Swiss roll, and we're going to generate 2 different kinds of combinatorial objects, which we then run through multidimensional scaling to do the embedding. So what we do is we take our data and we compute the pairwise distance matrix between all the pairs of points in the Swiss roll. And for one of the distance matrices, we add, some Gaussian noise to only 5% of the distances. And the other matrix we leave alone. Okay, for both of these matrices, we construct the 30 nearest neighbor graph based on these distances. And we then compare these graphs, and we note, hey, there are only 8.5% of the edge weights in this graph that are different from the edge weights in this graph. Surely these graphs cannot be that different from one another. Then we say, okay, how isomap works is it computes distances, then it computes the nearest neighbor graph, take k to be 30, and then you have a nearest neighbor graph, and then it applies multidimensional scaling to embed the graphs into 2 dimensions. And so that's what we did. We took the 2 graphs, one of which differs from the other by only 8.5% of the edge weights are different. They've been perturbed. And then we run MDS and we embed them. And you get 2 very different pictures. One of them looks reasonable, and the other one looks terrible. So these small changes in the distance matrix have led to just awful behavior in the downstream algorithmic results. And these perturbations are not the kind of perturbations that are somehow taken into account by analysis, current existing analysis of isomap. Isomap says, there are some results, roughly speaking, that say if I have noise in my data, have like a fuzzy manifold, then running isomap is actually not so bad. But here, this is something quite different. This is saying, somehow the geometry I have perturbed in some weird way, and that completely destroys the performance of the algorithm. So it's like perturbing the geometry versus perturbing the data points. Something, it's quite different. So I got interested in these kinds of problems from sort of a couple of different reasons. One of them was I sat through a bunch of talks and realized, all of these machine learning algorithms, they all depend on the quality of the metric representation of the data. There are even, it's fairly well known in, so there are well-known examples in theoretical computer science, say graph algorithms, or clustering algorithms, where if the distances do not satisfy a metric, your approximation algorithm has very different properties from an approximation algorithm that is run on distances that are guaranteed to be a metric. So traveling salesman problem is one of the canonical examples here. And so I thought, I know this phenomenon exists in more computer science-y as opposed to machine learning algorithms. And maybe this is also true of machine learning algorithms as well. Also, somehow the idea that, whatever metric I use to represent my data, somehow it should capture salient features of the data. Somehow, if the data are sort of all clumped over here, but there's one thing over here, I really need to know like, what do the distances look like over here versus here? And that somehow there's some tension in capturing the features of the data versus like exploiting the specific geometry of the space in which we represent the data. And I know I was also sitting through a bunch of talks on single cell RNA sequencing data, where to mathematicians, the data are big matrices, number of cells by number of genes, and the entries in the matrix are like frequency counts, how frequently this one gene is expressed in this cell. And these matrices are incredibly sparse. They're like 90, depending on the sequencing modality, something like 90% sparse or 85%. And so, whatever kind of distance you would like to compute between cells to capture the geometry of cell space, whatever kind of distance you compute, it's a mess. The entries in the distance matrix are, it's incredibly corrupted. The distances don't satisfy, the values that you get don't satisfy a metric. It's a mess. And yet people, then want to run clustering algorithms and dimension reduction on these kind of data sets. And it's tricky when, the input is garbagey. Okay, so I'm going to talk about three representative problems in sort of this large space that I call metric learning, although I know that metric learning is the name of a particular kind of problem, which is going to be an example of metric learning problems. So here are the three problems. So the first one is called metric nearness. And some of you may have heard me talk about metric repair. It's like a specific example of metric nearness. So in this problem, you're given a set of distances or a matrix of distances between points, and you want to find the closest metric or the closest matrix that satisfies a metric to the given matrix of distances. So closest could be here in some LP norm for reasonable P. It could also be the closest in L0 norm, i.e. what is the fewest number of distances I need to change so as to ensure that the distances all satisfy the triangle inequality. So there's a very concise, nice statement for metric nearness for the L0 norm, but what is the closest metric in some LP norm to the given matrix of distances that I'm given? There's another example in this area called correlation clustering. And here, the difference between a data set and a graph is sort of negligible. I'm given vertices on a graph, and I'm told which vertices are similar and which ones are dissimilar. And I want to partition the nodes in the graph so that all of the similar, as many of the similar ones are in one node, are in one cluster as possible. And the nodes that are dissimilar are in two different clusters. Then there's also sort of a data version or a point set version of this problem, which is known as metric learning. And it says, suppose I'm given a data set and I'm given information about which points are similar and which points are dissimilar. Is there a metric that is consistent with the dissimilarity information about the data? So it puts points that are dissimilar at far away and puts points that are similar close together. What is a metric that is consistent with this information? So in order to formulate these problems more precisely so that we can talk about algorithms for these problems, I'm going to give you some definitions, and along the way I'm going to point out handy features of these definitions, and then I can state precisely a bunch of these problems, and we can talk about the optimization problems that underlie these problems. So first of all, my notation, D is going to be a distance function. This is from x cross x into R. Capital D is a matrix of pairwise distances. You know, my data set is X, and I talk reasonably interchangeably about the data set X and the graph, the weighted graph that's induced by the data set. You know, I associate data points with vertices, and I have edges between data points, and the weight of the edge is conveying some kind of information about the relationship between the points, like they're similar, or, you know, this is how far apart they are, or, you know, some kind of information like this. And then I'm interested in collections of distances amongst data points that satisfy a metric. So I'll let the audience remember for themselves what are the definitions? What is the definition of a metric? You know, everybody can remember, oh, not all distances are a metric. So I'm interested in the space of all metrics on n points. That is a polytope. So I'm going to call met of n the metric polytope on n points. And then, since I'm also interested in graphs induced by a data set, I'm interested in the metric polytope that corresponds to the graph G. And so I'm just going to let you know the definition is that this is the projection of the metric polytope onto the coordinates given by the edges of the graph. Okay, I can't really wave my hands and do a polytope for you, but in not more than 3 dimensions, but there we go. Now imagine, you know, you project onto coordinates wherever you have edges. Okay, so those are the definitions. I have seriously waved my hands, and I want you to observe that there's a nice geometric, so there's obviously a nice geometric definition of a metric polytope. There's also a nice geometric description of this metric polytope for the graph. And you can see that it is the intersection of possibly exponentially many half spaces. So, okay, I'm going to wave my hands and go like this. These are intersections of half spaces. What you should be thinking in trying to parse this definition, blah, 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 if for all edges in the graph, the distance on the edge should be greater than or equal to 0. Oh, good, that check, that's part of my definition for a metric. And for every cycle in G, I have that the cycle is not broken. This is the analog to broken triangles. So the triangle inequality has to be satisfied for a metric. A triangle is a cycle of length 3. And to say that a triangle is not broken says that the sum of these 2 edges is longer than the edge from here to here. I can't do this without waving my hands. So this definition here is the cycle version. Imagine sticking in many more edges, and this edge cannot be longer than the sum of all the other edges. So that's this cycle condition here. And I'll let you check that, yes, the metric polytope on G is an intersection of exponentially many half spaces, and they're all sort of given by these cycle constraints. This is the analog of triangles cannot be broken for a metric. Okay, so let's go talk about these specific problem formulations. So I'm going to do this in some weird order. The first one is correlation clustering. Here I'm given a graph G and dissimilarity measures on each edge. So it's a weight saying, how much the 2 vertices that are at the ends of this edge are similar and how much they are dissimilar. And you want to partition your nodes into clusters so as to, let's say, optimize this function I want to make sure that those nodes that are similar are together and those nodes that are different are apart, and I want to set these values 0 and 1 so as to minimize this objective function. Okay, so this is a way of formulating correlation clustering. Unfortunately, solving this formulation is hard. And so what people typically do is relax this formulation. This is an integer program. They relax this formulation to say, the weights or the partitioning of my nodes should be a soft partitioning. So I want to have values in my partition between 0 and 1, not 0 or 1. And I want these distances that are between 0 and 1 to satisfy triangle inequality. So here I have the same objective function as before, but now I have different constraints. So I've relaxed the constraints to be anywhere in the interval from 0 to 1, and I want these distances to satisfy the triangle inequality. Okay, the metric nearness problem is very easy to state with all of these, with all of this notation now. Given a matrix D, an n by n matrix of distances, find the closest metric to the given distances. So find the m that lives in the metric polytope that is as close as possible in some LP norm to D. Okay, you could make this p 0, but then that's a whole nother talk. You can make this p between 0 and 1, and then it's this talk. I have highlighted in red sort of a different extension or idea for this problem, and that is, what if instead of insisting that you find the closest metric, what if you go for something like a tree metric or a hyperbolic metric? In other words, what if instead of asking for a generic metric, you wanted some kind of special conditions, like you have a tree metric or a delta hyperbolic metric? Okay, so I put that in red. I will come back to that at the end. I will not tell you how to solve this problem. That's, again, a different talk, but it's an interesting idea. Okay, so, then there's I forgot, there are 3 problems. There's the metric learning problem, and I have called this the general metric learning problem because I want to highlight that it's different from, well, it's different from the original statement for metric learning problem, and it's different from all of the 80 bazillion variants that came after the original metric learning paper. And it's different in the sense that we seek a metric, a generic metric. So, okay, so let me back up. So for metric learning problem, we have a data set. We're given a set of similar data points, and we're given a set of dissimilar data points. And we seek a metric, a generic metric M, that lives in the metric polytope that is sort of faithful to this notion of similar and dissimilar. And one way to capture that fidelity is to say, look, we want to find the metric that minimizes this, this objective function. Between points that are similar, the metric should be small. Amongst points that are dissimilar, the metric should be large. And those of you who are not familiar with this, with the first variant of this problem, I'm going to tell you that this differs from the standard variant of the problem in that we seek a generic metric M as opposed to a linear transformation of a Euclidean metric. So that is the standard formulation. It basically, says, hey, I take, I seek some, beautiful diagonal quadratic form, as opposed to a generic matrix, a generic metric. we go for a much more general problem for metric learning. Okay, what do all of these problems have in common? They can all be formulated as the following kind of objective function. So we want to minimize some, okay, the strictly version, the strictly convex function, the strictly is in there so that I can talk about theoretical results. I need the convex part so I can do algorithms and have guaranteed theoretical results, but please do not get too hung up on the strict part. I'm not a strict person. So given a strictly convex function and some graph G, again, this is quite generic. The graph could be the complete graph on n data points. Some family of half spaces that perhaps captures additional, is encoding additional constraints, like for the correlation clustering problem that the distances xij have to be between 0 and 1. Then we seek a unique point, we seek the unique point in the intersection of all of these constraints, okay, that minimizes this convex function. All right, so wait, hold on, we got to parse this again. Okay, I want to minimize some convex, strictly convex objective function subject to a bunch of inequality constraints. And in particular, a bunch of metric constraints. Ignore this ax less than b for a second, because that's just like additional stuff. But I want to minimize a convex objective function subject to a whole bunch of metric constraints. All the distances should satisfy some kind of metric constraint on metric condition on my graph G, or G might be the complete graph. Okay, now you might be saying, you might be calculating, I'm done parsing that, Anna, and I can calculate that that met n of G is big. And in particular, I might have, even in the simple case, if I have n data points, I have roughly n cubed triangle inequality constraints. N cubed is a big number. And when I add in the graphs, I might have exponentially many for graph cycle constraints. Then this is not so good for solving optimization problems, even if it is convex. There are too many constraints. N cubed is not good. So you might say, well, okay, fine, I'm going to sample my constraints at random. In a not very intelligent way, just sample them at random, and I will say, yes, you could do that, but you will end up having to run too many iterations. I'm going to say coupon collector and let you think, oh, how many times do I have to sample in order to see all of the constraints? You have to sample a lot. Okay, and to sample a lot means I run a whole bunch of iterations. Okay, you say, how about Lagrangian formulations? Well, they really don't help with the convergence or sort of scaling up to the big size. You have to do something different. Okay, so what is it that we are going to do? I claim that we have a generic algorithmic approach for solving these kinds of problems. And what do I mean by these kinds of problems? I mean convex optimization subject to a whole bunch of metric constraints, like a whole bunch of inequality constraints, possibly exponentially many. And this is an iterative algorithm. It is like an active set method. I mean, an active set method is like a generic way of saying, hey, we don't look at all the constraints. We only look at the ones that are active. And for those that are active, for those that we need to do something about, the algorithm has two parts. One is the algorithm is called project and forget. You do a Bregman projection onto the appropriate constraints, and you do it in such a way that you don't have to look at sort of all of the constraints cyclically, which is a problem with existing methods. And then after doing the Bregman projection onto the appropriate list of constraints, the algorithm forgets those constraints for which we haven't done any updates. So again, this is a way of getting around, not having to mess with all of them. What can I tell you in a summary about the theoretical guarantees for this algorithm? Well, it converges to the global optimal solution. And with the appropriate hypotheses on the strictly convex function, we can talk about the rate of decay of the optimality error, that it decays exponentially, asymptotically. We can also guarantee that when the algorithm terminates, the set of constraints are exactly the active constraints. I can also tell you that we have a stochastic version, a stochastic variant that does not simply just sample the constraints. You're going to say, well, this sounds like you have, solved the world's problems. How do you do this? You need an oracle. You need a separation oracle that will tell you which constraints are violated. And you need one that runs in polynomial time. And if you want a stochastic variant of the algorithm, you need a randomized oracle, or an oracle that has probabilistic guarantees. So that's how you get the stochastic variant. Okay, so you need a separation oracle. And then there are these two other components of the algorithm. So I'm going to walk you through the pseudocode at a high level, and we can go from there. So the algorithm is called project and forget because there are two main components. You do a Bregman.
Can I ask a quick question?
Yes.
If in practice, what would you replace your separation oracle with? Would you have sort of a guess for the violated constraints, or if you run this on your genetic data, for example?
No. I have an actual separation oracle for the metric violations.
Oh, okay. That's what is it? It's the sort of
data.
That's
the next slide.
Got it. Okay, then I'll shut up.
No. The quick answer, Mark, is all pair shortest path. Okay, so this means I'm going too slowly. Okay, so the algorithm comes in three parts. So while you're not done, you first get a list of the violated constraints, i.e. you first figure out what triangles are broken, and where are my metric violations. You add those to your current list, and then you project onto the boundaries of the half spaces that are in your list. This projection is a Bregman projection, so you come down here. This is the project part, and here I've written out what the Bregman projection actually is. Unless f is quadratic, I think there aren't sort of nice, beautiful formulas for a Bregman projection, but here I put in some pseudocode. So you do the projection, and you accumulate in these dual variables, how much you updated things. And in the forget step, you go and you check. Did I actually update this variable or not? And corresponding to my constraints in my list. And if I didn't actually have any net updates, then I forget it. I eject it from the list, and then I continue. Okay, so that's the sort of high-level architecture of the problem. Mark rightly asks, what is the separation oracle? Okay, so, and like in practice, how do you do this? So, these, as I have said, these constraints may be numerous, so writing them down is expensive, and it's best to access them only through a separation oracle, which will, what is this? So this is a deterministic polynomial time algorithm that says, hey, given a bunch of half spaces, it says whether or not a given point X is in this intersection, or or it returns a list that gives you some some that tells you your point is so far away from it. A stochastic version is we have a random version of this, produces a good list with high probability. Okay, so that's what a separation oracle is. This is kind of a generic definition. Give me an example. So in particular, give me an example for metric violations. So I want to know which of my distances fail to satisfy a metric or fail to adhere to being a metric. These are the ones for which the triangle inequality is broken. And so how do you check whether or not the triangle inequality is broken? You do a comparison to what is the shortest path between 2 points in the data set. And if you have a broken triangle, add it to the list. Okay, so here is an algorithm that gives you an oracle. I will let you do your check in your head as to how quickly, to verify how quickly this can run. I will tell you, you should think about all pair shortest path on different kinds of graphs. Okay, so I claim that this is a separation oracle for metric violations. Okay. All right, and then a little bit of sort of annoying reminders or first time through. What is a Bregman distance, a generalized Bregman distance for a convex function, which here is the definition. What does it mean? This is a generalized Bregman distance. What does it mean to do a Bregman projection? Well, it's a point that minimizes the Bregman distance from your point Y onto a closed convex set C. So it's like a standard projection, but different distance measurement. Okay. So armed with these definitions and algorithmic components, we can prove a theorem with several parts that says this is a good algorithm if various hypotheses are satisfied, like if f is a nice function and these hyperplanes are strongly zone consistent with respect to f, then the algorithm converges to the optimal solution of the problem. And if you know nice things about your function, then you can say something about the rate at which this algorithm converges. You also can get out of the proof of this theorem that at the end, if your constraint AI is inactive, then if at any point it goes inactive, then these dual variables Z are 0 for the rest of the computation. So like you're really only finding the active constraints in the algorithm, right? This is all fine and good and an ugly proof. It's actually not all that interesting a proof. What is more interesting is, does this actually work? Yes, it does actually work. So it's like, this is a case where working in theory says nothing and working in practice is like really what matters. On the other hand, it's nice to know that the working in practice is not like, some special case. So, okay, so I'm gonna show you some experiments from a couple of these different versions of these problems, and I'm going to start off with the correlation clustering first, and this is the weighted version of the correlation clustering, not the NP-hard problem, not the integer programming version. Remember, this is a partitioning of vertices in a graph. So you can ask, is this a dense graph or a sparse graph? Because you're going to get different performance depending on which is which. So first, we're going to start with dense graphs. So we're going to do weighted correlation clustering for dense graphs. And Velt et al. Showed that like standard commercial packages like Gurobi optimization packages, they run out of memory at about 4,000 nodes on a 100 gig machine for this problem. No, okay, fine, great, whatever. They developed a method that will scale up to roughly 3 times bigger size graph. They have a different formulation of their optimization problem. When this scaling parameter gamma is big, these formulations are equivalent. But notice they have a convex objective function subject to metric constraints. Metric constraints on the complete graph. So this is exactly the kind of problem that we can tackle. And so we were able to do a head-to-head comparison, exactly their problem on exactly the kind of graphs that they could do. And so we picked 4 different graphs from the Stanford network repository and compared our project and forget from their to their code. We compared running time, quality of the solutions, like what is the approximation ratio, and how much memory do you use for these graphs. So I'm going to tell you that Ruggles et al. Ruggles is the first author on, it's Ruggles, Velt, Gleich. The other one is Velt and Gleich. This is a parallel implementation of the Velt algorithm. And we took 4 dense graphs from the Stanford network repository, and you can see how big they are. They run from 4,000 nodes to 11,000 nodes, which is what Velt et al. Said they could handle. And what we see is that the time that our algorithm takes is considerably shorter than the time that the Ruggles algorithm takes. Our approximation ratio is better, so we get somehow a better optimality ratio. Somehow it's a better solution. Where we don't do as well is in the average memory usage per iteration. So we went and we looked at this, and this is a result of taking an average. So what you can see is that in the first few iterations of our algorithm on these kinds of problems, the number of constraints returned by the oracle is really high. It's like 10 to the 7.5. And then after 10 iterations, the number of constraints goes way down, and by the time we get out to 15 constraints, we have found the active set of constraints. But when you take into account the average memory that's used over all of these iterations, these guys add a lot. They contribute a lot to the average. But it is true that we do find this active set, and you can see how quickly it hones in on which things need to be adjusted. And you can also check the maximum violation of a metric constraint really does seem to decay quite quickly over the iterations. Okay, so that's dense graphs. We are better than what was state of the art for these kinds of graphs. Better, but truth in advertising, if you go look at the average memory usage, yeah, sort of, it's more complicated what's going on in the memory usage here. Okay, dense graphs, that's nice. Anna, however, those are small, and many real data sets, graphs, are very sparse, and they're huge. So how well do you do solving weighted correlation clustering on sparse, huge graphs? And we do incredibly well, actually. So again, I actually forget if these are from the Stanford Network repository or not. They're called /dot and e-opinions. I'm sure they are huge social network graphs. They have 82,000 and 130,000 nodes in them. And so that leads to 10 to the 14th and 10 to the 15th constraints for metric constraints. And our algorithm was able to solve these correlation clustering problems in, granted, 46 hours is kind of long, 120 hours is long too, but it worked. And you get, here's the optimality ratio. You can see that the number of active constraints is actually considerably smaller than 10 to the 14th. This is what, 1, 2, 3, 4, 5, 10 to the 6th, 10 to the 5th. It's considerably different. And,
how do you compute the optimality ratio? You know what the optimal answer is? Or
yeah, I guess so. Yeah, it may also be a function of one of the variables that falls out of the optimization criteria function. I actually forget. It's not that you can compute the optimal solution. Okay, so that's correlation clustering on sparse and dense graphs, including ones that are huge, that are just cannot be touched by existing software or state-of-the-art software either. Okay, so the next problem that I'm going to talk about is metric nearness experiments, and these are much more sort of proof of concept, because the right thing to compare against is an algorithm from about 2004, 2007. This is a paper by Brickell et al. I think it's dated 2007, but I know the work was done in 2004. So we implemented their algorithm. And okay, so here's the problem. You're given a matrix D of distances amongst endpoints, and you want to find the closest metric in, let's say L1 to the given matrix. And the matrix M that you find, that you want to find, it must satisfy a metric, and all the triangle inequalities have to hold. And so we cooked up two different kinds of complete graphs. We took D to be a random binary distance matrix, and D to be a random Gaussian distance matrix. So we got two different kinds of graphs, and then compared against Rishi's implementation of the Brickell et al. Algorithm. And what we can tell you is that the average time taken by our algorithm is less than that taken by Brickell's algorithm. How much less? It actually kind of depends on what kind of graph it is, whether it's a random binary distance matrix or a random Gaussian distance matrix. But we do better, at least averaging over 5 trials. Certainly, this plot shows considerable difference. Okay, so in the paper that Rishi and I have been working on, we have other examples of these kind of metric constrained optimization problems that we can solve, and how well we do against sort of specialized algorithms for those particular problems. And so I'm not going to show you the results, but one example I have here is for solving what are called L2 SVMs. So, solving a support vector machine using a L2 norm. And there's a package called liblinear, which is one of the standard, there's a very specific purpose software for these L2 SVMs. And our algorithm is as just a plain sort of generic algorithm, not a special purpose one for L2 SVMs, is competitive with liblinear. Basically,
Anna, I have a question from Cullen Hasselby. He wants to know, if you add a new row to the data, do you have a way to quickly update the resulting metric? And you add or delete rows to D and update the answer quickly.
We might be able to do that for the metric repair problem, which is one I did not discuss, but I did allude to. I don't know for these optimization things. Yeah, I don't know, but I suspect you might be able to do something like that for a very specific version of the metric nearness problem. Okay. Okay, so I said somewhere in the middle of this talk, it might be interesting to constrain your distances to some kind of special metric, like a tree metric or a delta hyperbolic metric. I started this talk with an example of taking a data set, building a combinatorial object like a graph, and then using that combinatorial object to embed the data set in a lower dimensional space. And we started to think about this for embeddings into hyperbolic spaces, because hyperbolic spaces seem like quite useful ways of representing your data to extract hierarchical information or to learn something that's more representative of the geometry of the data than simply embedding into Euclidean space. We saw examples of this in analyzing single cell genomic data to try and do sort of lineage tracing, or less fancily phylogenetic trees. Reconstructing phylogenetic trees, this is certainly true, and there's certainly these kinds of questions come up in linguistics and social network analysis. You want to extract some notion of hierarchy in your social structure. So we have work, which I will not talk about, but say, this is something that we're currently working on, using a bunch of these ideas to go from data or distances to a combinatorial object that's a special kind of graph, that's a tree, and then embedding the tree not in Euclidean space, but embedded in hyperbolic space. This is one of the different new directions that Rishi and I are working on right now. And that is a nice extension of sort of these ideas that I started the talk with. So at this point, I'm going to end. I think I have 5 minutes for questions. Is that right?
Yes. Technically, I guess you have as long for questions as you feel like letting people ask you questions. But 5 minutes sounds good.
Well, I was like, that's always the case, but I wasn't sure how long I was actually supposed to go for.
Yeah, no, that's good. So thanks a lot for the talk. If anyone has additional questions for the Q&A, feel free to put your question in there now, and we will ask them on your behalf. And I will turn off the recording now as well.